If we're looking to find the absolute max and min of a function, we are using the extreme value theorem, which requires that the function is continuous. So the first thing that we have to notice here is that x to the 2/3 power, because that's a cubed root, it's defined for all real numbers. Same with 20 minus x, that's a polynomial. So f has domain negative infinity to infinity. So it's going to be continuous on the interval from -1 to 20. I have to state that in order to use the theorem, that it has that continuity. Now we know that the maximums and minimums occur either at the endpoints or the critical values in between. So to find the critical values, we're going to take the first derivative. So before I do that, I'm going to rewrite f by multiplying that x to the 2/3 through and make that 20x to the 2/3 minus x to the 5/3, because I'm going to add my exponent, 2/3 plus 1 gives me that 5/3. So now the derivative, f prime, would be 40/3 x to the -1/3 minus 5/3 x to the 2/3. If I rewrite that, that would be 40 over 3x to the 1/3 minus 5x to the 2/3 over 3. So to get a common denominator, I have to multiply the second fraction by x to the 1/3 over x to the 1/3, and we get 40 minus 5x to the 2/3 plus 1/3 is x to the first over that common denominator, 3x to the 1/3. Now setting the denominator equal to 0, 3x to the 1/3 equals 0, gives me x equals 0. And setting the numerator equal to 0, 5 minus 5x equals 0, that gives me x equals 8. Those are my two critical values, x equals 0 and 8. So now to find the max and min, we're going to plug in the endpoints and the critical values in between to the original function and see what is the biggest and what is the smallest. The biggest is my max, the smallest is my min. So if I look at -1 to the 2/3 power times 20 minus -1, that would be 21. And if I plug in 0, I'm going to get a 0. Whoops. And if I plug in 8, I'll get 8 to the 2/3. Well, the cubed root of 8 is 2, squared is 4, times 20 minus 8 is 12, so that's a 48. And then 20, I'll have 20 to the 2/3 power times 20 minus 20, which is 0. So notice that my absolute max is 48, and the absolute min is 0. That's my highest and lowest y value I get back. All right, let's look at the second problem here, which is problem 4, number F. If I plug directly in, sinh of 0 is 0, minus 0 would be a 0 over x cubed is 0. So this is a 0 over 0 form, and I can apply L'Hopital's rule. So I would have the limit as x approaches 0, derivative of sinh is cosh, derivative of x is 1 over 3x squared. Plug directly in, and I get cosh of 0, which is 1 minus 1. So that's a 0 over 0. So we're still in indeterminate form. We can again apply L'Hopital's rule. Derivative of cosh is sinh over 6x. And we're again in that 0 over 0 form. So doing it one more time gives me derivative of sinh is cosh. Derivative of 6x is a 6. Cosh of 0 is a 1, so this is a 1/6. And if we look at this one, plugging directly in, cosine of pi over 2 is a 0. Secant of pi over 2 is an undefined. So this is a 0 times infinity form. We've got to rewrite it in a 0 over 0 or an infinity over infinity form in order to use L'Hopital's rule. So we're going to rewrite that secant as cosine of 5x in the denominator. So now at pi over 2, cosine of pi over 2 is 0. Cosine of 5 pi over 2 is 0. So we're in a 0 over 0 form, and I can apply L'Hopital's rule. Limit as x approaches pi over 2 from the left. Derivative of cosine is a negative sine x over negative sine of 5x times 5 by the chain rule. Plugging directly in, sine of pi over 2 is a 1, so that's a negative 1 over negative sine of 5 pi over 2. Okay, we've got to figure out sine of 5 pi over 2. Go to our unit circle. There's 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2 is back at a positive 1 times 5, so that will make a positive 1/5. Okay, and our last one is x to the power of e to the negative x. Let's see if we can make this a little bit bigger, get a little more room on the screen here. Well, that'll help a little bit. There we go. All right. So now if I go to evaluate this, as we plug in infinity, I would have x is infinity. E to the negative infinity goes to 0. So this is an infinity to the 0 indeterminate form. So we know with that, our tool is to rewrite it using a logarithm. So if I have, that's got to be an exponent there. Whoops, let me erase. There we go. X e to the negative x, and I take the natural log of both sides, I'd have natural log of y equals natural log of x e to the negative x. So that exponent comes down in front using my laws of logarithms. I'm not doing a derivative, we're just doing the laws of logarithms. And so now if I'm calculating the limit as x approaches infinity of the natural log of y, that would be equal to the limit as x approaches infinity of this e to the negative x ln of x expression. E to the negative x, we said, goes to 0. Ln of infinity would go to infinity, so we're still in that 0 to infinity form. So to get it into the form we need for L'Hopital's rule, we're going to put that e to the x in the denominator, make that natural log of x over e to the positive x, right, because that negative exponent puts it in the bottom of a fraction. Now I'm in an infinity over infinity form, and I can apply L'Hopital's rule. Limit as x approaches infinity, and derivative of natural log is 1 over x, derivative of e to the x is e to the x. We'd rewrite that as the limit as x approaches infinity of 1 over x times e to the x. That's how we'd clean up that algebra. And now if I plug directly in, we have a 1 over infinity, and we know 1 over infinity goes to 0.